I posted the first lab assignment on the Blackboard. Okay, in this lab assignment, you are requested to install virtual machines on your computers. Okay, your laptop or your computers. You can install the virtual machine platforms on your machine, and you need to install the Linux operating system. So actually, in this lab, in this course, we will use the Ubuntu-based operating systems. So I recommend you install the Ubuntu. Okay. So if you read the lab document, then I believe so you can figure out how to install the Ubuntu operating system. Okay, so as I announced in the first class, so we will not teach about how to use a virtual machine or how to use Ubuntu. Okay, so if you are not familiar with how to use Ubuntu or some tools like the VirtualBox or VMware, then you need study by yourself. And so actually in the lab document, I provide the links to the tutorials. Okay, tutorials for installing virtual machines or tutorials for installing Ubuntu. Okay, so so if you are not familiar with the Ubuntu, like the Linux commands, then you can visit this link. Okay, so this link. Okay, so and then please follow the tutorials on this link. And actually, I believe most of you are using Windows operating systems or Mac operating systems. Okay. And then so I also provide some information for the Windows users and Mac operating system users. Okay, you can find these instructions. Okay, so for Windows users, I recommend you install WSL. Okay, so if you are using Windows 11, then you can install WSL very easily. Okay, so you can click this link, like for WSL, you can click this link and then you can follow the instructions about how to install WSL on your Windows operating system. So if you install the WSL, then you can use the command line interface on your Windows machine. And then you can also install. Actually, for this lab, you are requested to install the validator and GTK Wave. So you know the GTK Wave is the GUI, the graphics user interface application. But if you are using WSL, then you can launch the GTK Wave very easily without setting up the desktop managers. Okay. So for Windows users, I recommend you to use WSL. So and then also you can install virtual machine platforms such as VirtualBox. Okay. So if you want to install the full operating systems of Ubuntu-based Linux, then you can use VirtualBox. Okay. So, so please read the lab document thoroughly. Okay, it's very important. Okay, and then for Mac users, okay, so I believe the Mac users can also use command line interface, and then so actually you can install validator and GTK wave very easily on your Mac machine. But actually the next lab, so you are requested to install the RISC-V GNU compiler toolchain. So actually this toolchain will work on Linux operating system. So I recommend you also, so for Mac users, I recommend you to install the virtual machine platforms such as VMware Fusion or UTM. So recently the VMware Fusion becomes a freeware for the personal use. So you can use the VMware Fusion without payment. Okay. So but for the Mac operating system, so for Mac users, so you need to install Ubuntu Server for ARM. Okay. So if you are using Apple Silicon, so Apple Silicon uses ARM instruction, some ARM ISA, so instruction set architecture. So let's see. So you can find that Ubuntu Server ARM, so it's for the Apple Silicon users, and then Ubuntu Desktop for x86, it's for Intel Silicon. So I know the old MacBook, an old MacBook uses Intel chips, okay, Intel CPU. And then, you know, the Intel CPUs use x86 ISA. So ISA is different. So the recent Apple machine uses ARM ISA, and then but the old generation MacBook uses the Intel CPUs, and then ISAs are different. So we need to use the different operating systems for the some different ISA, so different CPUs. Okay. So if you are using the recent the Apple Silicon, the MacBook that includes Apple Silicon, then you need to download the Ubuntu Server for ARM, okay, because the ISA is different. And then if we are using the old MacBook that includes Intel CPUs, then you need to download the Ubuntu Desktop for x86, okay, it's different. Okay, and then you need to set up the virtual machine platforms like VMware, and then you need to install the Ubuntu operating systems on your VMware or UTM. And then so if you install the Ubuntu server, not desktop, and then Ubuntu server just provides the command line interface. The Ubuntu server does not include the desktop managers. Okay, but one application. So in this lab, so we use GTK wave, and then as I mentioned, the GTK wave is the GUI application. So GTK wave requires desktop managers. Okay, so if you install the Ubuntu server, then you need to also install the desktop manager. Okay, so this is the instruction. So all right, my finger is not working. So this is the instruction to for installing the desktop manager on your Ubuntu server. Okay, so if we are using Mac operating system, okay, so this the modern MacBook, and so firstly you need to install the Ubuntu server for ARM, and then you need to install the desktop manager. Okay, so like the except the CE4. So this is the preparation. So and then as I mentioned on the this lab document, if you are using Ubuntu now, then you can skip this prerequisite section. Okay, so this section, so this section, then this section provides the instructions how to install Ubuntu operating system on your Windows or Mac machine. Okay. And then, so if you are not familiar with some of these installation processes, then you can get help from TAs. Okay. Also, for the first lab, so actually the first lab is provided for preparing the following lab assignments. So actually, in the first lab, you need to install the Ubuntu operating system on your machine, and then you will be requested to install EDA tools. So, as I mentioned in the first class, so we will use some tools that can simulate system value. Okay. Okay. So, so for the upcoming lab assignment, so you need to use some EDA tools such as Validator and GTK Wave. So this lab provides some instructions how to install Validator, but don't worry, it's very simple. Okay. So if you successfully install the Ubuntu operating system, then you can install the Validator using this one-line instruction. Okay, so it's very simple and it's very convenient. I think it's more convenient than Windows or Mac operating system. Okay. And then using Validator, so I also provide the sample system Verilog module. Okay, so N2 design. So in this design, so this is the system Verilog module. Okay, and then so this is the complete module. Okay, so in this N2 design, the N2 receives the 2 inputs and then it generates 1 output. Okay, two bit input signals and then it generates two bit output signal. Okay, so this very simple system Verilog module, and you can compile. So this module, this RTL file is just a text file. Okay, it's just a text file like your normal text file, such as some normal text file. So it includes only characters or letters. Okay. So in order to simulate this system Verilog module, then you need to compile this system Verilog module using Verilog. Okay. So this is the command. So you can just execute this command for the compilation. And so this code is a little bit long. It's longer than the design module, but in order to simulate the system Verilog design, we require test bench. Okay, so I will also provide some video links for the system Verilog lectures in what I taught in the previous semester. So actually, so we require test bench to execute this compiled design. Okay, so I also provide this test bench file. Okay, so you can copy and paste, or you can type the test bench file, and then also you need to also compile the test bench file using validator. Okay, you can find the validator command here. Okay, and then you can find that the design file and test bench file is compiled. Design the system Verilog design module and the test bench file. It's a this is the C++ file. Okay, so very interesting. So and then you can compile test bench file and then system module using Verilog. So if you are interested, then you can also visit the some Verilog page. Okay, so actually this is the so the Verilog is the free open source compiler for system Verilog or VHDL, some other HDL, so hardware description languages. So this is a compiler, okay, and Verilog translates this HDL modules the module written in system Verilog, HDL or system C. So Verilog translates this module into C++ file. Okay. So then we can compile. We can compile C or C++ using C compiler or C++ compiler. Then we can generate the binary file, right? So this is the process, and then we will learn about this compilation process in today's lecture. Okay? So actually, when we compile our design modules and the test bench file using Verilog, then interestingly, binary file is generated like the other compilers, other C or C++ compilers, and then we can execute. We can execute this generated binary file like the normal binary file. Okay. So if you type the source code and then test bench file correctly, and then if you compile these files also correctly, and then if you execute the generated binary file, so this is the generated binary file, then you can see the output like this. Okay, so you can find that also in a test bench file. You can find printf. Okay, so this is the printf statement in C. Okay, so actually printf generator is display lines. Okay? Also, if you execute the generated binary file, then the binary file will generate the BCD file. So you can find the wave.bcd. Okay, and then this BCD file includes the waveform information. Okay, and then if you execute the GTK wave, then you can see the waveform using GTK wave like this. Okay, so this is the simulation process using Verilog. So if actually in lab 4, 5, 6. No. All right. 1, 2, 3, 4. Lab 4, 5, 6. Then you will be requested to design a RISC-V processor with system Verilog. Then so you need to use the validator and GTK wave. Okay. So this the first let us lab assignment is required for the following lab assignment. Okay, so you need to you need to get familiar with some of this environment, like the Ubuntu operating systems and virtual machine and EDA tools such as Ventilator and GTK Wave. Okay, so this is so you want to do. Okay, and then so if you I repeat, so if you are not familiar with this environment, like the Linux operating system and then some EDA tools and then command line interfaces or virtual machine, then you can get help from TAs. So you can post any questions on Piazza, okay? Then TAs will have, then TAs will also answer your questions on Piazza, okay? Also, I provide the TA's office information, right? The information about the TA's office, then you can also stop by TA's office by appointment, okay? Okay, so this is very important, okay? This is the first level assignment, and then you actually you need to prepare some environment for the following lab assignments, okay? Okay. So okay, so we are in the new chapter. Any questions? Okay. So in the first chapter, so we learned about the performance metric of processors, right? So this is very important. So actually, you need to memorize the how to calculate the CPU time. So like this. Then in midterm, so you will be asked about how to calculate the CPU time. Okay. So now, so the chapter 2. So in the chapter 2, we will learn about the instruction set architecture. So, and then we will use the RISC-V ISA. So RISC-V instruction set architecture. Okay. So what is the title of this chapter 2? The language of the computer. So what does that mean? So what is the language of a human? It's English or Korean. So actually it's called the natural language. Okay. And then actually for programming, we use programming languages. And then these languages are called high-level languages, right? We can understand, humans can understand easily high-level languages. So you need to learn. So in order to use some natural languages, we need to learn these languages. It's okay. It's same. It's the same. So for programming, we need to learn about the programming languages, and then after that we can easily understand. So we can easily understand the meaning of syntaxes or statement and some functions. But how about the computers? I mentioned that the CPU, the processor, the CPUs are kind of digital systems, and then a digital system can only understand 1 and 0. It's a binary signals. Okay, so what does that mean? The high-level languages needs to be translated into this binary code. Okay, right, and then actually, so before translating into this machine code, then we also define the assembly code. Okay, this assembly code codes are represented using letters like alphabets, but these assembly instructions can be mapped to the the binary instructions, so binary code. Okay, so instruction set architecture defines these assembly instructions and how to translate assembly instructions into machine code, so binary signals. Okay, so this is the instruction set architecture. And then based on this instruction set architecture, CPU vendors design CPU hardware. Okay. So in chapter 2, we will learn about this instruction set architecture. Okay. This is also an important chapter. Okay. So can you see? So as I mentioned, so this is the instruction set. So it's a group of instructions. Okay. So instruction set architecture also represent the group of instructions. So instruction set. And then under the instruction set, you can find the hardware. Okay. And then for the on the instruction set, you can find the software. So what does that mean? Instruction set is an interface between software and hardware. Okay, this is an interface. Okay, and then hardware is the standing, and then hardware is a lifting of this instruction set. So on the plane of the instruction set, you can find the software guys. So they are playing. But hardware is just out. Okay. So you can just understand that the instructions. So instruction set is an interface between software and hardware. Okay. So an intermediate language or intermediate code. Okay. So before learning about the instruction set architecture, then we need to define processor or processor. So what is a processor? The processor is a machine that executes instructions. So this machine is also called a computer system. So what is different? So I believe I also explained about this this definition. Okay, so we can differentiate the normal TV or smart TV, right? So what is the difference? Smart TV includes a processor that can execute instructions defined by instruction set architecture, right? And then instructions are translated from high-level language code. This is a computer, okay? The difference between the normal electric devices and a computer is a computer can execute instructions defined in instruction set architecture. So you can understand the computer or a processor because a CPU execute instructions is a CPU. Okay, so you can understand a CPU like this. So instructions are input to CPU, and what is the output? What is the output of CPU? Change of state. So what does that mean? So, okay. So instructions. So instructions look like this, like add x1, x2, x3, or load x1, and x2 and offset, or other instruction like and instruction, logical and x1, x2, x3. So RISC-V instructions, like RISC type instructions, look like this. What is this? Actually, instruction set architecture define the operation by instruction. So what is the operation? So what is the result of this instruction? Like x1 is x2 plus, okay, plus x3. And then load is means that x1 is equal to, it reads the memory, and then x2 plus 0. And x1 equal x2 and logical and x3. So you can understand instructions like this. Instructions define the operations by a processor. Okay. So then there are many different types of instructions for the computers. Okay, like so we will learn about the RISC-V instruction set architecture. So it's a RISC type ISA. The RISC-V is the RISC-V ISA includes the RISC type instructions. So there are different types of instructions such as arithmetic logic, or data transfer, and control instructions. Okay, so we can define instructions, and then actually these instructions are input to processors. Processor received instructions. Okay, actually, so we can these are assembly instructions. So actually, these instructions need to be translated into machine code. Okay, like 1010 the binary codes. Okay, then what's the meaning of change of state? So if you see the operations, the definition of instructions, then you can find that the result. You can find the result of instructions. Okay, like so you can find that x1 is equal to x1 is equal to x1 is equal to. So what does that mean? The value, the data in x1 is changing. Okay, I said the data in x1. Okay, so you can understand how x1 is similar to variable in programming languages, right? So we can store a certain data in variables in the program code. Okay, so we can understand x1. Oh, x1, so data in x1 is changing. So it means the change of state. Okay, so actually, when in the ISA, instructions defined in ISA just change the register files and main memory. So what does that mean? X1 is the register. Okay, so we will learn about the register later. Okay, so you can just understand that register is the very small memory space. Okay, and then the data can be stored in these registers. Okay, So as you can see, instructions can change the data in registers. Okay, and then register file represent the group of registers. Okay, how about the main memory? So if we use the store instruction, so in the previous slide, I just showed the arithmetic instruction, the add instruction, and data transfer instruction, like load instruction. Okay, but you can find that load also changes the data in X1. But if we use the store instruction like X1, X2, and offset, it represents memory addressed by X2 plus 0 becomes the X1. So this is the definition of for instruction. So what is changing? So you can find the memory. And then this is the address of memory. So it means the data in memory is changing. Okay, so you can find that this is this is an array, right? So memory is just an array, okay, data array. So you can find that if you see this definition, then you can find that the data in memory array is changing. Okay, and then the index is the X2 plus 0, right? So instruction can change the data in main memory. Okay. Okay. So you can understand it like this. So processor or CPU receives instructions. Then CPUs generate the output. Then what are outputs of CPU? Outputs of CPU are changes of states. Okay, but it changes data in register files or data in memory. So you can understand like this: a processor or CPU receives data, so received instruction, but instruction just changes the data. It's data in register file or memory. This is a CPU, and then this is a computer system, right? So you can understand the CPU like this, okay? So it's a black box, receive the instruction, and then it generates the change of state. Okay, so we will learn about how instructions are defined for the CPU. Okay. Okay, so I will explain about instruction set architecture. So I also mentioned the x86 or ARM. Okay, and the x86 or ARM is the different types of ISA. Okay, so the instruction set architecture defines the instructions for different kinds of CPU. So for example, x86 ISA is used by Intel CPUs or AMD CPUs, right? So Intel CPUs and AMD CPUs can execute instructions defined by x86 ISA. Okay. Then if we just provide the ARM instructions, okay, so different instructions to these Intel CPUs and or AMD CPUs, Intel CPUs or AMD CPUs cannot execute these instructions. Why? Intel CPU can only execute instructions defined by x86 ISA. Okay. How about the Apple? Okay, so ARM. ARM CPUs can only execute the instructions defined by ARM ISA. Okay. If the x86 instructions are provided, then the Apple CPU, the ARM CPUs cannot understand these instructions. That's why I explained. So if your Mac computers, if your Mac computer includes the Apple Silicon, it includes the ARM CPU, so it implements the ARM ISA, then you need to download the Ubuntu for ARM, right? Then if your MacBook includes the Intel CPUs, then you need to download the Ubuntu for x86. Okay, that's why I explained like this. Okay, the ISA defines the CPU or CPU family, like the x86 CPU or ARM CPU. And then it is a collection of instructions. Okay. Also, ISA defines how memory is organized, and then how instructions are translated, and then how CPUs need to be designed. Okay. So what is the ISA? ISA is the contract between software and hardware. And then based on this contract, then software is also designed, then hardware is also designed. Okay, that's why ISA is very important. So you need to understand how instructions are defined and organized for CPU and for a computer system. So actually the ISA defines the CPU family, and then traditionally when we mention a computer architecture, then it mentioned the instruction set architecture. Okay, but we can also use the terminology architecture with the different meaning. So I believe you have heard about some Skylake architecture or Haswell architecture, Broadwell architecture, or Lunar Lake architecture. So what is this architecture? So I mentioned that traditionally, when we mention a computer architecture, it means instruction set architecture. So we can say that, oh, this CPU uses the x86 architecture. But sometimes we can use the terminology architecture with the different meanings, such as I mentioned, so this is the Skylake architecture. This CPU is designed using Skylake architecture or Lunar Lake architecture, Raptor Lake architecture. What is this architecture? The CPU architecture. So it's also called micro architecture. Okay. So like the Skylake or Raptor, this is the code name of the Intel micro architecture. So micro architecture defines how hardware is designed. Okay, but Skylake or Raptor Lake or some other Intel CPUs can execute x86 ISA instructions. Okay, when you mention the x86 architecture, then it defines the x86 ISA. Okay, so it means these CPUs can execute x86 instructions. But sometimes we mention the microarchitecture of CPU, such as the Skylake or Raptor Lake or Coffee Lake, something like that. Then this architecture represents the microarchitecture of CPU. Do you understand? So you need to distinguish the instruction set architecture and microarchitecture of CPU. Okay. Instruction set architecture is just to define the many instructions. So there are many instructions in the defined by instruction set architecture. So we will learn about some RISC-V instruction set architecture in this course. So you can find that this ISA includes the hundreds to thousand instructions. Okay, so you can just understand that instruction set is the repertoire, the list of instructions that can be executed by a CPU. Okay, then we learn how RISC-V instructions are organized, how these instructions are executed by a CPU. Okay, so I mentioned there are some different types of ISA, like the x86. The most popular ISAs are x86 and ARM ISA. And in this course, we will learn about the RISC-V instruction set architecture. Okay, it's a RISC-V. Okay, so why? So RISC-V is the open source ISA. So what does that mean? What is the open source ISA? So for example, so Samsung can make a mobile processor like Exynos, right? And then Exynos is designed by Samsung, but Exynos uses ARM ISA. So what does that mean? Exynos is designed to execute ARM instructions. And then ARM is not an open source ISA. So what does that mean? Samsung needs to pay royalty to ARM. It's not free. x86 is the same. x86 is developed by Intel. So in order to use x86 ISA, then the CPU vendors need to pay royalty to Intel. It's not free. But RISC-V is the open source ISA. It's free, and then we can use the instructions defined by RISC-V ISA. Also, we can define new instructions, new custom instructions in RISC-V ISA freely. Okay, so this is the open source ISA. So RISC-V was developed by UC Berkeley. Also, it was developed by David Patterson and John Hennessy, the authors of the textbook, right? And then, so actually, RISC-V is very simple and it's the RISC type ISA. So I frequently mention RISC type. So what does that mean? RISC represents the reduced instruction set computer. And then also we have the CISC type ISA. The CISC represents the complex. C means the complex. Then ISC is the same. So again, the RISC is simpler than CISC type ISA. So CISC is the x86. x86 ISA is the CISC type ISA. Okay, so RISC-V is the RISC type ISA, so it's simple. Okay, and then it's also clean. Okay, so what does that mean? Clean. So actually, the x86 has very long history. Okay, so you know the Intel CPUs have long history. So actually, the Intel have added the new instructions in x86 ISA. So it means there are many instructions, and then the instructions are very complex. Okay, but RISC-V is recently developed, so it's still clean. Okay, so it also includes the smaller number of instructions. Okay, let's see. So if you are interested, you can also click the slide and video links for the RISC-V ISA. So we can also compare the x86 ARM or RISC-V. So as I mentioned, the x86 is the CISC type ISA. It's too complex. It's very complex actually. And then it's not free. Okay. Also you can find that x86 ISA includes 1,300 instructions. Okay. More than 1,000 instructions. Okay. So which means if the CPUs need to execute these 1,300 instructions. Okay, so complex, right? Then instruction length. So we will learn about the instruction length. So actually, the RISC type ISA usually have the 4-byte instructions, but you can find that x86 ISA, the instruction length is the 1 to 15 bytes. So it's not simple. Okay. How about the ARM? ARM is simpler because the ARM is also RISC type ISA. Okay, but it's not free. It includes the 400 instructions. So around 400 instructions. And then RISC-V is designed for research, education, and commercial. Okay, it's open source ISA. It's free and RISC type ISA, and it's clean. So simple and clean state, and then also another feature is the modular ISA. So it means based on the base integer ISA, then we can add more instructions for supporting more complex instructions. So and then actually in this course we will learn about the RV32I instruction set. Okay, so this is the basic, and then base integer ISA. So what is the meaning of integer ISA? Integer instructions. What is the meaning of integer instructions? Integer instructions handle integer data. What is integer data? Integer, 알죠? 정수. Okay. So integer instructions handle integer data. Then it's simple. Okay. So RB32I just list the integer instructions supported by RISC-V processor. So this is the common and basic instructions. Okay, common and basic. And then this number represents the 32-bit computers, or 64-bit computers, or 128-bit computers. Okay. So in this course, we will learn about the RV32I. It's a basic ISA. And then based on this basic ISA, we can add more complex instructions. Okay, so these are called extensions of RISC-V ISA. Okay, so M represents the multiply. So we can add multiply instructions on the RV32I. So then it is called the RV32IM. Okay. So if we just add multiply and divide instructions, then this is we can add the M extension. So and then A represents the atomic memory operation, F represents the floating point instructions. Okay, E double precision. Okay, and then G is the general purpose. General purpose represents the integer, multiply, atomic, and single precision and double precision floating point. Okay, so in the second lab assignment, so you will be requested to install RISC-V compile toolchain. Okay, so and then if you install this RISC-V compile toolchain, then actually you need to define like the IV32I or IV32M, IV32A like this. Okay, so it means so we can add or we can remove some instructions in the RISC-V instruction set. Okay, so just to remember that IV32I, so it's an integer based integer type ISA is the baseline, so basic and instructions, and based on these basic instructions, we can add more instructions using extensions. Okay, MAFD. Okay, so this is also a comparison. Like ARM and RISC-V. Then okay, you can find that RISC-V is simpler. Okay. And then this is the reference card of RISC-V, and then this reference card shows some instructions, the part of instructions of RISC-V. Okay, so we will learn about these instructions in this course. Okay. So now I'll explain how a high-level language code is translated by compiler. So you can find it translation and starting of program. Okay. So as I mentioned, the CPU cannot understand high-level language code. It is just a letter, and it is just an alphabet. Okay. So this high-level language code needs to be translated into binary code. Okay, 101010. Okay, and so for this translation, we use compiler. So usually a compiler composed of compiler and assembler. Okay, compiler generates the assembly code. Okay, and then this assembler translates the assembly code into machine code. Okay, so this is the two-step process of a compiler. So then this is the final shape of our program. Okay, our program includes the instructions like this. Okay, and then these instructions are translated into the machine code like 101010, and then it's saved to the digital data. So what does that mean? So if you see this machine code, then you can find that, oh, this is the, actually we cannot distinguish between the instructions and binary data, right? All all signals are 1 and 0. Okay. So actually I want to explain about the full program computer. What does that mean? Stored program computer represent that our instruction, our code is also stored in the memory of a computer, like other binary data. What does it mean? So we can easily think that our data, like the image data or the some text data can be stored in the memory, right? Because the data is actually in the computer system, so the all data is binary data. Okay, we can represent the image data or text data using binary code or binary signals, right? And then this is our data, and then we already know that, oh, memory is used for storing data, right? How about programs? How about instructions? I mentioned a program, but actually a program is a group of instructions. It's a bundle of instructions, right? How about a program? Program or instructions are also stored in the memory. So this is stored program computer model. Why? Because you cannot distinguish it. So the instructions are also represented using binary signals or binary data. Also, we can represent our normal data using binary signals. And then all binary signals are stored in the memory of a computer system. Okay. So what does it mean? Actually, our instruction, our program code, and then our data are all stored in the main memory or DRAM of a computer system. Okay. I said the main memory. Okay. It means it's a DRAM of our computer system. So our code or like the machine code, and then our data all are stored in the main memory. Then how can we access the data or instructions in main memory? How can we access the data? So if we write the code, so like A equal 1 and B equal 2, then we can access the data stored in this variable. But this is the software concept. But in the hardware, I mentioned all data and then all instructions are stored in the memory. And in order to access the data in memory, then we need to use an address. Of a memory. Okay, so what is an address? So what is a memory? So I mentioned that memory, you can understand the memory like the data array. Then how can you access the element in data array? You can access the data in array using an index. Right. So for example, let us assume that A has the 100 elements like A0, A1, A99. Okay, so there are 100 elements or there are 100 data space in the data array A. Then how can you access the element, one of the element in this data array? So we can use the index. So this number 1, 0, 99. So these are indexes. So we can access the data like the A1. Okay. You can understand a memory like this. In a computer hardware, a memory includes the data space. Okay. Any data spaces. Okay, like the memory 0, memory 1, and then memory F, 0x of f. So memory includes many data elements and store many data elements. And then in order to access the data element in the memory, then we need to use the index of memory, right? And then what is this index? Actually, we call these indexes as the addresses. Okay, this is an address of memory. Okay, understand? So, 컴퓨터. So, so I explained the actually all data and all instructions. All instruction codes are also stored in the memory. Then how can you access the instructions? First, how can you access the data in memory? We can use addresses, right? We can like the index of the memory, then we can use an address to access a certain memory element, right? And then I also mentioned that instructions are stored in the memory. Then how can you access these instructions? Using an address, right? So I said that this is a computer model, right? So instructions are given to a processor or CPU, and then CPU generate outputs like a change of states. Then actually CPU read instructions from memory using an address. Okay, so like the in order to read this instruction, so the CPU read the memory 0x0010. So instruction is stored in this memory space, and the instruction is given to a processor, and instruction is executed. So this is called stored program computer, right? So actually we are familiar with this stored program computer model, but actually initially the first computers such as ENIAC and then some other the first mainframe computers did not implement this stored program computer model. Okay, so actually, so stored computer program model is developed by von Neumann. Okay? So he's a genius of the computer computer field. Okay, so you need to understand that instruction or program codes are also stored in the memory, and then using a memory address, then CPU can access instructions in the memory. So this is the stored program computer model. Okay, it's like this. So this is the example of RISC-V assembly code. Okay, so we can get this code by compiling high-level language code using RISC-V compiler. Okay, so if you see this code, so this is the assembly instruction, and then actually these are machine code represented using hexadecimal code, hexadecimal number. So you can find that this is the hexadecimal number, like 0x. And then you can also find a certain number here. Okay. So what does that mean? Actually, this is the address in memory. And then this is an instruction. So what does that mean? This instruction is stored in the memory addressed by 10074. Okay. And then this memory space stores the FD010113. Okay. So a CPU reads the data, the FD010113 in the memory using an address 10074. Then this is an instruction like add SP minus 48. Okay. Then CPU execute this instruction. Okay. So the address of instruction like 10074 is called program counter. Okay. And then it's also called the PC, program counter. So why did I show this? Because actually you need to understand how instructions are stored. And using program counter, it's an address of an instruction. Okay, so you need to understand this. Using a program counter, CPU accesses the instruction in the memory. Okay, so I mentioned access, it means read. Then if a CPU reads instructions using a program counter, then CPU can execute an instruction. That's how a CPU execute an instruction. Okay, so you need to understand the PC. It's very important. Okay, program counter. Program counter is an address of an instruction. Okay. Okay. So I stop here. Any questions? Thank you for your attention and see you in the next class. 감사합니다.